Okay. So this is the third in the rheology lectures. You heard last week from Phil Scammer, who gave an introduction on rheology and rock deformation, and then Uli Fowle gave a talk yesterday about rheology and focused a lot on deformation more in the diffusion regime and how that relates to seismic attenuation. And so I'm going to talk today about rheology, looking at how we relate measurements of seismic anisotropy to what we see in mantle samples and what the relationship is between this seismic measurement that we can make and what is going on at the microstructural level. So this is, again, focusing on rheology in the ductile regime. So compared to what we saw in the previous talk this morning, I'm shifting us back down deeper into the subduction zone system, into the area where things are flowing by a ductile mechanism. There is certainly a lot related to rheology that was discussed a little bit this morning in terms of the rheology at that plate zone interface, but what we're going to focus on now is what's going on in mantle flow in a subduction zone setting and what the constraints are from field samples in how we interpret the seismic observations that we have. So this is a photomicrograph of a prototype. This was actually collected from the Tonga Trench from a depth of about 8 kilometers. It is an unusually fresh seafloor sample. You guys saw in the tutorial, the geology tutorial last week, you saw some of these samples that we have from the Tonga Trench. These are one of the few places where we have FORARC samples really collected in situ. But what I want to focus on in these samples today is largely the olivine, which is most of what you're seeing in this image. There is a little bit of orthopyroxene in this sample, and there are trace amounts of spinel that are not visible in this image. Olivine here, you will see this gradation in the colors. That is an indication of subgrain boundaries. That is an indication of the deformation that has gone on in the sample. So when we are talking about flow in the mantle, we are looking at samples like these that are relatively coarse-grained, but they do have a lattice alignment, and this is something that we can measure and we can link to the seismic properties. So I'm going to start out and give you an overview of why we care about this in the subduction zone setting, and then I will go into detail about how we look at these samples and how we relate those samples to the seismic properties. So this is an olivine crystal with it's an orthorhombic crystal, and it has 3 principal axes referred to as the A, B, and C axis, or also the 100, 010, and 001 axis. And I will use both terminologies in this talk. Raise your hand and ask me questions if it's not clear what I'm talking about as I go along. The key thing to take away from this image is that the A-axis in olivine is the seismically fast direction, and the B-axis is the seismically slowest direction, and the C-axis is intermediate. So this is, in terms of understanding seismic anisotropy, this is the key aspect, that you have an anisotropic mineral, and that the seismic waves will propagate at different speeds depending on which direction it goes through the mineral. The other important thing is that during flow in the mantle, if you're flowing by a dislocation mechanism, then you will end up having a crystallographic preferred orientation, also referred to as a lattice preferred orientation. That indicates that you have slip on a specific slip system in olivine. So in this case, what I'm showing here is what we call often the A-type slip system, also called easy slip for olivine. And another way to talk about it is actually identifying what that slip system is. So this terminology, 100 with the square brackets, indicates the slip direction. So it is slipping in the 100 direction, or the A-axis direction. And then the 010 indicates the slip plane. So the plane that it is slipping on, outlined in red, is the 010 plane. And the way that we figure this out in looking at natural samples is looking at the pole figure, which is plotted at the bottom here. So this is an olivine pole figure showing this easy slip system. The maximum, so this is just a schematic, so this is showing a maximum approximately aligned up with the shear direction, so that is the slip direction. And this that is normal to that shear direction is the slip plane. And then the 001 plane, or the C-axis, is not dominant in this slip system. So this is the fact that when olivine is deforming by a dislocation mechanism, it results in an alignment because it is dominantly slipping on a slip system such as this one, is what is giving rise to seismic anisotropy in the mantle. And so we have this general model for the upper mantle that in the asthenosphere we have flow that is reflecting the current plate motion, and that will result in an alignment of the olivine A axis because that is usually the slip direction, and that is also the fastest, seismically fastest axis. And then as you go to shallower depths in the mantle, we expect to get fabrics that are frozen in. And so this is the general schema, the general conceptual framework that we work on when we're interpreting the fabrics in olivine-rich rocks. And then this can be related to seismic anisotropy, and I am benefiting now from the fact that Ed Garnero posts a lot of images on his website, including this nice little GIF showing what happens if you have an incoming seismic wave that is goes through an anisotropic medium. So your collection of olivine crystals, as long as they have a relative crystallographic alignment, that is an anisotropic medium, and that will result in this shear wave splitting that he is showing here. So the end result of that is that you get this delta T, which is something that the seismologist can measure and tell us a lot about in terms of what the splitting is, the magnitude, the direction. And so this has been, this was hypothesized going back to the 60s that there should be seismic anisotropy, and there was a very nice experiment done on the East Pacific Rise in the 1990s. So this is one example of the results from this experiment. This is the ridge axis coming down here, the East Pacific Rise. So we are way out somewhere in the Pacific Ocean with the Pacific and Nazca plates spreading apart from each other. And these are the shear wave splitting measurements that were made by Wolf and Solomon, and you can see that they are lined up approximately perpendicular to the axis. And so that agrees with this model that the olivine A axis, the seismically fastest axis, records the direction of mantle flow, and because flow at a ridge should be going perpendicular to the ridge axis, seeing that this shear wave splitting, that the alignment was like this, was a nice corroboration of this model. So, you've all had coffee. Pop quiz. At a subduction zone, an example being here the Tonga subduction zone, where you have two plates converging, what would you expect to be the orientation of your seismically fast axis of the shear wave splitting? Do you expect it to be parallel to the subduction zone or perpendicular to the subduction zone? So raise your hand if you would expect it to be parallel to the subduction zone. Which side are you talking about? So if you would expect it to be either parallel, so this is the direction of plate convergence, and if you would expect it to be parallel or perpendicular. And let's just stick with the mantle wedge for now.
Where do you observe this?
I'm just saying theoretically, what would you predict?
At what point?
If you were looking at the splitting here over the mantle wedge. Or, I mean, you could also say over here as well, in this case. I mean, as a general, what orientation? Just raise your hand if you think it would be parallel to the subduction zone. If both your plates are moving, converging. Okay, and then if you think it would be perpendicular to the subduction zone. So the expectation, the plate motion is going towards each other, is that it would be, the answer would be B, right? And as many of you in the room know, what the actual observation is that it is, that we see this trench parallel direction. So this is the observation. This is the Tonga Trench over here. This is a figure from Smith et al. 2001, which Doug is a co-author on, so you can ask him questions about it. But the main observation I want to highlight is this trench parallel splitting that was observed. And in this case, this is on the size, this is on the mantle wedge side, but the observations have also been made on the opposite side, and they are also non-intuitive. So this is now non-intuitive? Counterintuitive. So, okay, this is now the compilation from Maureen Long and Torsten Becker's paper in 2010, summarizing all of the observations that have been made. And again, here is Tonga down here, and this is this really nice example where on both sides of the trench you have this trench parallel splitting, which is not what we would expect based on the fact that we expect the olivine A axis to be the slip direction, and to that to be more or less lined up with the plate motion direction.
Jessica, you were probably going to say that, but I think it's a fair statement that it's not necessarily everywhere trench parallel either, right? And we had a good discussion about that last week.
Okay.
And I think you can, it seems like the more data you add, the sort of more mixed up this becomes. And I think it's, one could make the argument that we don't know if it's truly anomalous everywhere, or if it's normal, or what normal should be.
Yes. So, okay. So Torsten's point is that, so Tonga, which I'm pointing out right now, is this really clear example. But if you go over here to the Andes, you do have a change as you go along, and you can, as you look around, you also, it is perpendicular here, Cascadia. It gets very messy over here. So there is also variation in the measurements that have been made, and so I will say now that where I'm going to end up with this talk is that it is complicated in that I would say 15 years ago we kind of were looking for this simple solution, and that is going to be this B-type olivine fabric that I will show you in a second. And then it also became clear from modeling that was done partly by Peter Van Kekken's group that that doesn't solve the problem because you also don't access that fabric type. And I think where it's being left off is that the flow field in these subduction zones is relatively complex. And there's modeling that's been done, including by Torsten, showing that you have very complex flow fields. And where we need to go with this, and this is where I'm going to end up in the talk, is coupling those two models that predict olivine fabric evolution and see if we can really match those observations using the current generation of modeling tools that are out there. So this is this observation now that is 7 years old, or I should say this is a compilation that Maureen and Torsten presented, showing these global observations that you do get this trench parallel splitting. You do also get some perpendicular, some stuff at various angles, and that that the flow of subduction zones, I think the consensus would be that it is a complex pattern, and that it has become, as I'm going to show you in the rest of this talk, that related to this, the rheology, we have the tools to do it, but there is still a lot that we need to do to understand how everything relates. So this is, so I showed you at the very beginning that the easy slip system in olivine, the most common slip system in olivine, is this A-type slip system, this 100 on the 010 plane. And then going back to 2001, there was a suggestion made that the way to explain this trench parallel splitting was to have this B-type olivine fabric. And so this is, again, just a schematic of showing what the pole figure would look like for that lattice preferred orientation of the olivine grains, and what that means in terms of the slip system. So in this case, you are slipping in the 010 direction on the 001 plane. And by doing that, because you're changing which is the dominant alignment and where the A-axis, your seismically fast axis, how that is aligned in the system, you can still have the trench perpendicular flow. It's just that you have you're accommodating that flow in a different slip system. And so you no longer have the seismically fast axis being aligned with the direction of flow. And that's the key to this B-type slip system, which is by having the A-axis in this orientation, it is no longer tracking your flow direction. But you can still, if you have type B flow, you can still interpret what the pattern of flow is if you are in this regime. And so another schematic from this review paper summarizing that is that with both, with these various types of fabric systems, so the olivine A-type or the B-type, the mantle flow direction in both these cases is the same, but what you're measuring in terms of the seismically fast direction is different because you have a different orientation of your olivine crystal lattice. And so the fast axis, the olivine A-axis, is now, in this system, is now oriented like this, but the flow is still going away from the trench in this scenario. So this was the hypothesis about, going back to 2001, that the way to explain the trench parallel splitting is that you do have flow going in towards the trench, as you would expect, based on the plate motion. It's just that the olivine A-axis no longer records the seismically fast, so it no longer records the mantle flow direction. This hypothesis has now fallen out of favor for various reasons. One of them is this modeling study that was done by Eric Nella with Peter Van Kekken, showing, so the problem with the B-type fabric is that you have to go to very high stress. And to get there, their models suggest that you can really only activate this fabric type if you go all the way up into the very nose of the mantle wedge, and that you need that really high strain regime to access that. And so that's one line of evidence why I would say in general people no longer favor this as the explanation for why you have this trench parallel splitting. Another thing, and this is what I'm going to spend time going into, is that we actually, one of the great things about that Jung and Corrado study, which developed this B-type hypothesis, is it kind of spurred people to start really looking back into fabrics again. And we now have this whole variety of different slip systems that we talk about in peridotite, and I'm going to come back and talk about this in more detail. But the take home from this slide is, so I showed you A-type and B-type. We now also have observations both experimentally and from field samples of these C-type, D-type, E-type, and there's actually a sixth type that we are finding often related to the presence of melt. So the way in which olivine aligns during flow, while it is true that this is the most commonly observed type, there are many field examples now where you are seeing a different type of fabric alignment. What this means in terms of seismic anisotropy, the real key thing is actually getting this switch where the A-axis is not aligned, is having the A-axis in this orientation to really change how you would interpret the mantle flow direction from the anisotropy, which is captured a little bit in this figure, because in this one they're saying if you have AC or E type, then your seismically fast direction is still the flow direction. So in terms of, you have to think geometrically about how, because your A-axis is the fastest, you always have to think about how this orientation, how that relates to the flow direction. And in some of these other slip systems, D-type and E-type, the A-axis is still the slip direction. And so in those cases, you don't expect to change. You expect the A-axis to map onto your flow direction. But where you have a change to, say, a B-type fabric is when you would really expect a difference in how you're interpreting the seismic anisotropy. So as I said a little bit ago, the general consensus is that mantle flow is very complex in 3 dimensions. And so this is this nice figure from Maureen Long and Paul Silver's paper, just showing that you have corner flow. You may also have 3D flow around the slab, and that the general take home from all of this work on the seismic anisotropy is that it's a much more complicated system. And so what I want to show you today is what it is about the olivine LPO side of things, what the observations are that we've had since this kind of flurry of activity on the shear wave splitting, and first of all, kind of how we get this data on the olivine, and then how we can use it to help us to interpret what's going on with these large-scale seismic observations. So I'm going to start out talking about deformation by dislocation mechanisms in olivine, and pick up where Phil Scammer left off last week in talking about these basic rheology aspects. And then I'm going to spend some time talking about how do we actually measure the crystallographic preferred orientation in rocks, what are the constraints, what are the ways in which we do it, and then looking again at this range of crystallographic preferred orientations that have been identified, and then finally talking about the ways in which we can incorporate all of this data that's come online about CPOs into mantle flow models and understand subduction zones better. Okay, so as a recap, the mantle, or the upper mantle, is predominantly composed of peridotite. So that is another picture of a hand sample here. And that rock, most of what you see in that kind of olive green is the olivine in it. It's 60 to 80% of the rock. And then the second most dominant mineral is orthopyroxene, which is the darker patches you can see on the hand sample there. And then there is some amount of clinopyroxene, spinel, and sulfide. So when we worry about the rheology of the mantle, we pretty much only worry about olivine, or we worry about olivine and orthopyroxene. Clinopyroxene, if it is present, is probably similar rheologically to the orthopyroxene. And these two things are present at such trace levels that they really are not impacting the rheology of this material. So we mainly talk about olivine rheology, and from lab experiments, we almost exclusively have measurements of olivine that are constraining the rheology in terms of the lab. But we do also try to get some constraint on how orthopyroxene is influencing the deformation. The reason that we really focus on olivine is that it is just constraining this rheology has been 30, 40 years of lab experiments and also field observations. And orthopyroxene is actually much harder to deform in the lab. It's harder to access the pressure temperature regime where you're in the right orthopyroxene structure. And it also turns out that if you start to deform these mixtures, that you are much closer to the melting temperature when you're at lab conditions, right? So when you put orthopyroxene in here, then you lower the melting temperature of the whole system. And so it makes, experimentally, it makes things much more messy. So the fact that we simplify the mantle to being olivine is not that we are not aware that orthopyroxene isn't there, but just that it's been a lot of work to get to the state that we are today in terms of lab experiments for olivine, and it's also a very non-trivial problem to look at these mixed phase rheologies. But there is some work out there looking at orthopyroxene as well. Okay, and so this is now a slide from Phil Schemmer from what he showed last week, and he talked a little bit about dislocation creep, and this is one of the typical schematics that is often shown to talk about the way that dislocation creep operates at the microstructural level, right? And this also gets back to one of the points that Uli did a really nice job of emphasizing yesterday, which is that we need these defects in the crystals to see all of the properties that are going on in terms of rheology, right? So in this example, there is a missing atom here, and that when you apply a stress, that results in the propagation of that dislocation through the crystal lattice. And so that is, in terms of flow in the upper mantle, our best estimate is that the deformation is by a dislocation mechanism. And so this is the underlying process that is going on as you're deforming those individual crystals. But as you do that, that also results in them, you preferentially slip on certain planes. So those LPOs that I showed, you're preferentially slipping in the easy slip system. In olivine, you're preferentially slipping on the 010 plane in the 100 direction. And so there are certain planes that are easier to slip on in an orthorhombic crystal or in an anisotropic crystal, and that is what ultimately gives rise to that lattice preferred orientation. So if you are having if visualizing these dislocations is a little bit complicated, we fortunately have this great set of experiments that were actually published in 1947 using soap bubbles in a dish of water that you can use to visualize this. So, okay, so this is a movie that I'm about to play. These are a whole bunch of soap bubbles. This is actually sitting in a Pyrex dish, so you will eventually see the writing on the dish. The green here and there's some green there are two plastic spaces that you can use to kind of push the system and make the dislocations move around. And so what you're going to see is that you will start to see these dislocations moving around as the whole system is moved. So you can see one going through there and other ones moving around. And there's a vacancy. So this is, you can play around and just keep poking this whole system. So in this case, the whole thing's separated, which is not an analogy to anything. It's really yes, yeah, so we now have a plate boundary interface. So don't take it that far. But seeing that, being able to look at these moving around this is what is happening in the crystals to our best estimate based on years of study of not just olivine, but any material in this dislocation regime. Okay, so this is another one of Phil's slides. This is the olivine flow law. This comes up over and over again when we worry about the ductile rheology. So this is the strain rate related to this pre-exponential factor, the stress, the strain-dependent viscous anisotropy that we won't worry much about today, but the stress, the grain size, water if it's present, melt if it's present, and then the temperature and pressure term. So this is the one equation that keeps coming up over and over again. And through the lab experiments, we can build these deformation mechanism maps. So this is, again, one of the slides that Phil Schemmer showed. This is grain size here on this axis. In microns, this is the stress, and these are contours for strain rate. And depending on the grain size in the mantle and also what the stress is during your flow, then you will be in various of these deformation regimes. So dislocation creep dislocation accommodated grain boundary sliding, and diffusion creep. We're not going to worry about diffusion creep today. If we were talking about shear localization and ductile shear zones at the plate interface, then we would start really worrying about diffusion creep, because this is, in the ductile regime, the way that we get to shear localization and very high deformation. But if we're talking about flow in the mantle, we are in either the dislocation creep regime, or more likely, based on current data, we are in this dislocation accommodated grain boundary sliding regime. So this intermediate regime, it has a grain size dependency, but it is a dislocation accommodated mechanism, and so you also expect to end up having a lattice preferred orientation. And that is summarized here. So this is just showing an aggregate of crystals that you're deforming, and that if you have dislocation creep, as you're moving around those dislocations, because you have preferential slip systems, you expect to get an alignment of your crystallographic lattice. In diffusion creep, when you're moving things around, you're moving everything by diffusion, and as Uli discussed yesterday, we think a lot of the diffusion is actually, it's accommodated on the grain boundaries, and we don't expect to see any lattice preferred orientation. So if our expectation would be that if the mantle was dominantly deforming by diffusion creep, we would not expect to see seismic anisotropy. So the fact that we do see this seismic anisotropy is one of the arguments that we are in some type of dislocation mechanism. And then there's this third regime called dislocation accommodated grain boundary sliding, often abbreviated as DISGBS. And this is both grain size dependent, as diffusion creep is, but it does produce a lattice preferred orientation. Yes?
So I've read in several places the deeper part. I read a few places that the deeper part of the upper mantle is often thought to be in the diffusion creep regime. Is that still assumed? And what would be controlling the boundary with depth of where you get into the diffusion creep zone?
So my understanding is that the current, the idea for the asthenosphere is that it is more or less 200 kilometers thick, starting below the plate interface, and that is where we see the seismic anisotropy signal. And below that, that disappears, but you're still in the upper mantle, and that is one explanation, is that you've transitioned into diffusion creep. Because this equation is really complex, it depends not just, so one way to get into diffusion creep is to really decrease the grain size. But the other things that become important as you go deeper is this term, and in particularly, the activation volume becomes really important when you go deeper. So another way to get into diffusion creep is to increase P, and I think because of the activation volume term, then you can also get into diffusion creep.
Yeah, I was just going to comment on that. For constant grain size, it divvies out like it should, like Jason says, based on the depth dependence of those parameters alone.
If this is being recorded, I'll just say that Torsten agreed with me. For the record.
For constant grain size.
Yes, for constant grain size, it's really that pressure term. And there is, it gets messy as well, right? Because there's also error, some of these terms are harder to constrain in the lab. And so, for example, there's a lot of error associated with that V term. One reason for 40 years of experiments just on olivine alone is simply that there are a lot of terms in this equation, and getting to the, say, higher pressure regime and getting a good constraint on that V term has been really difficult. But the current estimate in the end is that we should transition to diffusion creep. So we have at least these three mechanisms, and I should say also there is another mechanism called low temperature plasticity, which has in the last couple years received a lot of attention. It is also one that is harder to access in the lab to make measurements on, but there is a school of thought developing that actually that a lot of the lithosphere, the olivine, might actually be in this low temperature plasticity regime when it's deforming. But for our purposes today, we're not going to worry about that. And on this map that I'm showing you here, that low temperature plasticity regime is up here at very high stress, though that flow law might be rewritten soon. So this is, again, the deformation mechanism map. This is taken from a publication with Lars Hansen. This is showing grain size, again, in microns. So a millimeter is around 10 to the 3. right? And in a lot of the field samples that we have, the grain size is somewhere on the order of 1 millimeter. So this is an example, this cluster of data here are measurements that we made in field samples from the Josephine prototype for both the grain size and the stress. And based on our estimate that we are dry, melt-free, and that the deformation in this case was at around 1,000 degrees C, we calculate this deformation mechanism map for the flow laws, putting in all the parameters for that equation I showed earlier. And then for our samples, we had measured grain size, and we had estimated stress based, in this case, on a subgrain size piezometer. And so we end up that we are deforming somewhere near 10 to the minus 12 per second. So that's a reasonable tectonic strain rate. And it also, we end up kind of squarely in this dislocation accommodated grain boundary sliding regime. So to our best estimate, I mean, I think there's, for the kind of asthenospheric portion of the mantle and even parts of the lithosphere, we are in some type of dislocation mechanism. There is still a lot of back and forth about the dislocation accommodated grain boundary sliding versus dislocation creep, but that doesn't change really what we worry about in terms of the CPOs that are developing. Okay, so now I really want to show you how we measure the crystallographic preferred orientation in rocks. And how we make those measurements going from looking at field samples. And so one final link back to what Phil Schemmer showed last week. So this is another one of his slides. He had this nice summary of microstructural analysis. And so you can do a variety of things when you have samples of rocks, either the naturally deformed prototypes that we collect in the field or the experimentally deformed samples. So you can look at the grain size. You can look at dislocation structures. You can also do these EBSD measurements that I will go into, and you can ultimately look at the lattice preferred orientation of your samples. So if we want to do this with field samples, oh, and actually, sorry, one more terminology thing. So I've been switching between saying CPO and LPO. Those are the same thing. So crystallographic preferred orientation or lattice preferred orientation refer to the same thing. And there's just been this use of both terms in the field. Okay, so ways in which we get samples of prototite at the surface of the Earth, right? So the problem with trying to study the mantle is that the crust gets in the way all the time. So one of the most common ways to look at samples is to look at mantle xenoliths that are brought to the surface in basaltic lavas. So this is an example of some Hawaiian xenoliths. So these are them out in the field. They are coated with some of the basalt on the exterior. But if you break it open, you see this nice, fresh prototite in here. Another way that we can look at samples, and so the limitation on looking at xenoliths, because xenoliths are probably give us the best distribution spatially, in that there are a lot of places where you're getting, xenoliths, especially if they're kimberlitic, they can come up from very deep. So some of the deepest mantle samples that we have available to us are those xenoliths and xenocrysts coming up in kimberlites. And they often are, in cratonic areas or volcanic areas, you're getting them where you're not going to find the other types of exposures you get where you can get collisional, where the other types that I'll show in a sec. So xenoliths, there's probably the best spatial distribution globally for xenoliths. But the limitation on them is that you have no orientation information. So if you're worrying about rheology, and particularly if you're worrying about how the olivine orientation relates to the seismic anisotropy ultimately, you actually need to have some structural context for how you're interpreting the sample. And I'll show you the frame of reference that we use in a second. And the key thing is that we need to know what the foliation and the lineation is in these samples. And you can see, looking at this sample, that it's really hard to figure that out from these samples. And I think often the way this is done to some extent is assuming it, though there are some tools coming online that I think might improve the situation. And so because of this limitation, one of the other ways that we look at mantle samples, and one of the real advantages of this example, is going to orogenic prototypes or ophiolites, which are abducted pieces of crust and mantle, or sometimes just the mantle section, that you find in collisional environments. So this is the most famous ophiolite example, which is the Oman ophiolite, which is highlighted here on this map of Oman, which is the largest exposure that we have. This was abducted onto land. This is associated, the interpretation is that the mantle and crust you see here were once a spreading ridge, and then they became part of a subduction zone environment and then got pushed up when during collision. And so if you go here, you can do really nice detailed transects. So this is an example from Nick Dygert's work, now just focusing on one of the massifs that are present, where you can walk in, you know always where you are relative to the crust. So they're lavas and then sheeted gabbros, and then you end up in the mantle. So you always know your structural context, or at least the local structural context. And you can do your best job at relating the orientation of your samples to, in this case, even the orientation of the moho. And so you can really relate your olivine fabrics that you ultimately measure to how that orientation relates to that piece of mantle relative to the crust in the assumed paleo ridge axis in this case. The other places where we have peridotite abducted on land, but we don't have the associated crust. So we have less structural information in this context. So this is an example. We are down here at the moment in Berkeley, and this is the California-Oregon border, and this is the Josephine peridotite up here. So this is an example of these samples in the field. This is actually peridotite that you're looking at. If you're thinking that it should be green, the reason that it's not is that all peridotite that is not in xenoliths is pretty much always weathered, and so the orogenic and ophiolite peridotites, the olivine, the iron in them oxidizes and essentially rusts in the field. So when you look at peridotites in the field, you're always looking at these red or orange rocks. And so this is actually peridotite, and if you hammer off a piece of the outcrop, then you will see something that is darker in color. But this is what peridotite looks like in the field. So the Josephine peridotite is a really nice large exposure of peridotite. We don't have that because it has thrust faults boundary on all sides. We can't directly relate it to depth below the moho and the kind of paleo ridge orientation. But we can go in the field and, for example, identify this foliation, which you can see really nicely in this image. And we can take samples relative to that foliation, which is the way in which we ultimately want to orient our samples, is to know what the shear direction was. And so the foliation that we see around here is actually very helpful in this case. And this is something that is much harder to identify in those xenolith hand samples.
What's the scale on that?
No, this is like waist high. Somewhere I have a version with a hammer. Yeah. This is a very comfortable rock for sitting on top of and eating your lunch. This outcrop is called the lunch spot outcrop. Yes.
Just maybe explain foliation and lineation. I don't know whether you did that.
So the foliation in this. So foliation is a planar alignment that you see, or layering that you get. And so this is the foliation, and it's a foliation because you can follow it around as you go around that outcrop. And then a lineation would be like individual crystals that are stretched out, and that is the lineation. And so to do that, you really have to get up much closer and look at the outcrop to find the orientation of your lineation. And I will show some examples in a second of what the observations are that we're making on the outcrop. But just before I do that, I want to make this other point, which is if you really want to look at the rocks in their structural context and you want to look at the subduction zones or ridges, this is the problem. And the problem is that we do have peridotite exposures on the seafloor, but the water is in the way. And it is a limiting factor, right? So Oman and the Josephine peridotite are great, but we don't, we infer what their tectonic setting was when those fabrics and when the deformation occurred. And if you really want to have things in their present day context, you need to go to the seafloor. We do have pretty good tools at the moment to do that, right? So ocean drilling has been one way in which you can really get samples in situ, and when that core comes up, you have orientation information associated with that core. The limitation in that case is that drilling one hole is itself a very expensive proposition, so it's hard to go around and get lots of different samples or do transects or anything like that. Dredging, this is a dredge basket with a person for scale. So dredge basket is nice and big. It can bring up a lot of rock, but it is, so the dredge basket is a very efficient way to sample at sea, but obviously you lose any outcrop scale context when you do that. All you know is that you've sampled a kilometer of the sea floor. You might have sampled 1 outcrop, you might have sampled 10. But this is the most common way in which we have seafloor samples. For Tonga, we have a nice suite of prototypes, but everything is dredge. So we don't know, that is actually the challenge in trying to do any fabric work on the samples, is that we don't really know how they relate to the orientation that they're in the outcrop. And then if you do want to get at oriented work, using submersibles or ROVs, it is possible to sample with like seeing the visual of what you're sampling. The subs are actually not quite set up that you could really take oriented samples. The Shinkai is actually the best in that it gives you heading information and you can reconstruct it to some extent. But it's still, doing one dive is also very expensive, and it's actually hard to get a lot of samples. A good dive would be bringing up something like 10 samples in a day. So those are the limitations of trying to really look at the mantle in its setting, right? So we do have places on the seafloor at ridges and in trenches where you have exposures of the mantle. It is now frozen in lithosphere, but you do have direct exposures of the mantle. But the sampling is a little bit difficult. Okay, and so then there's this structural context that we need to look at samples in. So when we tell you the LPO of a sample, it is always relative, or it should always be relative to the foliation and the lineation in a sample. And that is because we want to be looking at the cross-section through your shear plane. So this is an example. This is just a hypothetical cube of rock that has a foliation, which is shown by these lines. So this is the foliation plane that you are seeing here. And then a lineation would be any stretched out feature that you see in that. So in the case of the prototype, it would simply be elongated crystals of your olivine or your orthopyroxene. And that is how you identify the lineation in these samples. And this foliation plane that contains the lineation, that is your shear plane, right? So that is, you're assuming that is where the orientation of the deformation. And when we look at the LPO samples, we want to look at the cross-section through that. And so in structural geology, we always orient our thin sections so that they are cut perpendicular to foliation and parallel to lineation. And that's a standard thing, not just looking at the mantle, but looking at any field samples of a shear zone or any deformed crustal rocks as well. That the frame of reference is always this XZ, sometimes it's called XY structural plane, which is the cross-section through your shear plane. So to do that, and so when, to close the loop on this, just when I show you this LPO, so we have cut our thin section plane, which is the gray one up there, and we have then gone and looked at the orientation of all the axes on that plane. And then we are plotting things up relative to that thin section plane. And so in this case, you're, in this figure that Luke Mell made, the A-axis is generally aligned with the shear direction, and so that is your slip direction. This is just a schematic of how we link going from this field sample to the thin section plane with a whole bunch of crystals in it, measuring the orientation and then plotting them up on the LPO. And I will show you in more detail how we actually measure that LPO. But this foliation lineation issue is difficult in the prototypes. So this is actually a relatively deformed sample from Oman. This is what we would call a protomyelinite. So it's associated with a shear zone that's thought to be a paleotransform fault. And the reason I'm putting it up is that this is a better example of being able to identify the foliation. If anybody would like to raise their hand and tell me if they see the foliation, they are welcome to do that right now. Yeah, so a number of people are giving me this hand signal. So, so it is something like this, and it is a little. It is harder to do off the photo as well, right? So when we're at the outcrop, we spend a while poking around. You want to ideally, right? You're trying to identify a plane of features, so you want to look on this side as well, and so you spend a while poking around, finding as many different faces as you can. And then I would also say that the lineation is something like this in the sample. But again, you would want to look at a couple different surfaces of your outcrop to determine this. So this is something that's associated with a shear zone. But in the mantle, the flow in the mantle, like all the prototypes that you see, those have all, we assume have all undergone some amount of mantle flow. And so the fabrics that we're talking about, these are much more subtle, much more coarse-grained features. So this is another example. This is a Harzbergite, this is kind of really at the outer limits of this shear zone. This does not have a lot of grain size reduction, so we don't associate it with this really high strain deformation associated with a localized fault zone. In this case, we are interpreting the foliation that we see here as reflecting the flow in the mantle. And so again, we identified on outcrop that we had something approximately horizontal that we're looking at. You can see the grain size here. This is not a very fine-grained rock. This is what ductilely deformed upper mantle. This is what we think it looks like. And so one final example is this one, which is kind of what most of the samples look like that we see in the field. I think all of these are oriented so that the foliation is approximately horizontal. But these are subtle features. It's not easy. Often we kind of do this by committee. You have a couple people in the field and you kind of discuss it back and forth. It's not a really obvious thing. If you're looking at kind of, crustal rocks, especially if you have micas, then it can be really obvious to find the foliation. If you're looking at myelinite zones, it can be much easier. But this is one of the difficulties in doing this. There is potentially a new technique that could really help, which is shown in this paper by Vasilios Shetzaris and the group at University of Wisconsin did this, have started doing this more routinely, which is to do X-ray computed tomography of samples and use that to identify the spinel fabric. And so what they're showing is a xenolith hand sample here, and then this is the tomographic image where the blue is, it's not all the spinel, it's kind of enlarged ellipsoids that they assign to each spinel grain to help them identify the fabric. And so then using that, they determined that this would be the shear plane, and so the relevant cross-sectional plane that they need is this one, which is the face on which they cut it. For prototype, the biggest limitation of this technique is that you can really only identify the spinel easily in these tomographic images because the contrast between the other phases in prototype, between olivine and orthopyroxene, is very difficult. They've got a very, they don't have much contrast difference when you look at them. This is the same as looking at a backscattered electron image for those that are familiar with it. And so the thing that's easiest to get out of this data set is the spinel. And so this assumes that the spinel shape-preferred fabric is accurately reflecting the foliation and the lineation in the rock. And it's not necessarily clear that it is. Spinel is sometimes its own mystery, and the way it behaves can be a little complicated. But I think this is a really promising way of at least trying to be more systematic, particularly with samples like this, right? And it's, another problem that we have, and this happens with seafloor samples as well, is that, this sample comes up, somebody else might have, just cut it in half to do some geochemical analyses on it, and so you're left with a half of the sample, and then you need to look at a couple planes to identify foliation and lineation, and so you're left with this tiny cube of sample. And so it can be, just the sample size can be really limiting in terms of doing this, orienting your fabric data the correct way. Okay, so this is kind of the dirty tricks of the trade that nobody will talk about when you go and see that LPO data. And so you have to always take it on faith that they have done a good job of figuring out the LPO. And then one other point to make is that in prototypes, the alteration can make doing this work really difficult. So this is in the lab last week, or the tutorial, you guys looked at some of these samples from Tonga that cover this full spectrum from being completely fresh to completely altered. So in our ideal world, all of our samples that we get would have this level of alteration. But of course, that's not the case. A lot of xenoliths look like this. I would say a lot of orogenic prototypes and ophiolites tend to look like this. And a lot of seafloor samples tend to look like the 3, 4, 5 spectrum. And actually, for that reason, so obviously with that, we have no olivine. You're never going to get CPO data. But you can do something with a sample like this. But this is one of the reasons that actually if you look at ridge samples in particular, there's almost no fabric work that's been done on them, because doing analysis of this, and particularly these days we want to do things automated, this requires really complex post-processing. And so that has been kind of another limiting factor, that people have tended to focus on these samples, but there are a lot of, that limits the areas that you can look at in some cases. Okay, and then in thin section, what are we actually looking at? So these samples, these are the examples of samples that have undergone flow in the mantle, and they will have a crystallographic alignment when you measure the crystal orientations. So that means that when you measure the orientation of this olivine grain and this olivine grain and this olivine grain, that they will show some general alignment, and that reflects the flow by a dislocation mechanism in the mantle. What you see in thin section, you see these are subgrain boundaries. This is also called undulose extinction. This grain here also has it really nicely. So those are subgrain boundaries that have formed because of the deformation that the rock has undergone. This sample is a little bit more deformed. This one is more deformed than this one. And there's a little bit of recrystallization that's gone on and some grain size reduction, but still relatively large grain size. So this is, when we're talking about kind of mantle rocks and LPO, this is what these things look like in thin section. These are, when you're talking about mineral alignment, these do have a mineral alignment, but grain size is on the order of millimeters, so you've got to zoom out and measure a whole bunch of grains to get at that mineral alignment. The general rule of thumb is that you need 200 grain measurements or more to get an accurate representation of the fabric. And it's also, if you look at a myelinite, it's obvious, you get hundreds and thousands of grains in just one field of view like this. But in this case, this is the mantle. It's relatively coarse grained. You've got to look at a lot of grains to get at the LPO. So fortunately, in the old days, this used to be done by U-stage, which is basically sitting at a petrographic microscope and for each grain finding its angles of extinction and doing that one by one. And that is obviously very time consuming. But the other thing is that there's a lot more information you get if you can actually map the orientation of not just every grain, but every kind of pixel in the grain, and look at the subgrain orientations and look at the relative misorientation between the grain boundaries, something that Uli was talking about yesterday. And so in the last 15 years, looking at LPOs has really taken off thanks to this technique, which is electron backscatter diffraction. So what you're seeing here is a scanning electron microscope. This is the sample chamber. The electron beam is up there. The rest of the electronics are down there. You stick your sample in this thing, and if you have an electron backscatter diffraction detector, it sits here. And we also nowadays run this with the energy dispersive spectrometer running as well. So EDS gives us composition. EBSD gives us mineral orientation. It's now basically trivial to collect both data sets at the same time, so we always get the compositional data at the same time because it helps us in processing and IDing mineral phases. The basis for this EBSD analysis, so this is an image in the SEM, so your electron beam comes down here. Your sample is sitting here. It has to be at the 70 degree tilt to see the diffraction pattern. And this is the EBSD detector, and that's the EDS. So this EBSD detector is a phosphor screen. When the electron beam comes down, it causes lattice diffraction in your crystal, and that lattice diffraction gives this image. And that is imaged by this, it illuminates the phosphor screen, and then there's a camera that takes a picture, and then there's great computer software that processes the whole thing for you. And so you end up saying out of this, you have this diffraction pattern, and you say, okay, this is, you identify the orientation of your crystal, and you say, this is the orientation of this olivine crystal. And so nowadays you can go across and you get hundreds and hundreds of points just by mapping across a sample. And so this now is an example of an EBSD map that Lars Hansen collected. This is one of the samples from the Josephine prototype, so relatively undeformed. And you can see it is slightly pixelated because we've set, I think we had a step size in this case of about 2 microns. So every 2 microns, we got a diffraction pattern. We figured out the orientation of that diffraction pattern. And so we can then plot up the data here. So this is showing you actually both the olivine orientation in green and the orthopyroxene orientation in blue. And they have their orientations, the relative it's a relative plot here. But these samples have all, we're looking at them all in a specific frame of reference that we have tied ultimately to the foliation that we measured in the field. So this data set has this spatial relationship that we know relative to how we sampled these samples in the field and then cut the thin sections. And you can also see this, that all of this cross-cutting stuff, that's the serpentine. And so we're not indexing it serpentine because it's a very soft mineral. We can never polish it well enough to get data off of it. But in this case, the serpentinization is not too bad, and we can extract out of this not just orientation, but the grain size, the subgrain size, and a whole bunch of other data that's really useful. Yeah.
From your experience or other studies, does the serpentinite tend to just erase and step over the original LPO to exploit it and form parallel to it? Or is there any relationship between the orientation of the serpentinite grains and the original fabric of the rock?
In these coarse grain samples, we don't tend to see a relationship. In fault zones, where we have much more grain size reduction and myelinite formation, we do think we see a relationship between the serpentine orientation and the fabric of the rock, and we think that probably relates to the overall applied stress of that fault zone. But in this case, it seems pretty random.
I apologize if you just said this. How do you define the shear direction relative to the foliation plane?
Oh, okay. I didn't actually say this. So this is an example taken from these small scale shear zones in the Josephine prototype. And in this case, we actually can, it's a shear zone that's about 100 meters wide, and we can identify the shear plane, and we actually can track the foliation bending into it and back out. So in this case, we have two independent measures of shear plane and foliation plane. I would say in most cases, we would be happy to just be able to identify the foliation, and we normally don't have this additional information. Okay, so then this is the LPO. From this example, this is the LPO that we end up getting. And if we interpret this LPO relative to the foliation, so the foliation is now plotted at this slight angle to the shear plane. The A-axis is approximately aligned with that. So we would say we are slipping in the A direction, and that the slip plane in this case is more or less the 010 plane, the B plane. So this is just a type A example, this easy slip system in olivine. But there is, and so this is kind of going from field observations to actually getting the LPO itself. In this case, this is very closely linked into spatial structural measurements that we made in the field. And we could take it one step further. This is not for that same data set. This is just an example from a review paper by Phil Skemmer and Lars Hansen, which is to say that nowadays it is very routine to take your EBSD data set and to calculate the elasticity tensor from that, and then to calculate what that means in terms of the splitting and the magnitude of the splitting. And that is almost always done these days in MATLAB, using this toolbox that has come online called MTEX. And that's a great resource that has been developed and made available to the community. And so you will see in a lot of papers that look at olivine LPOs that they go this step further and calculate the seismic wave properties as well. Okay, so that was kind of the nuts and bolts of how we get at CPOs and what the limitations are in field samples we can get, and also what the measurements are that we're making in the lab of these samples. And so then I start out by saying, initially we all, everybody said, well, there's kind of this easy slip system in olivine, that's the dominant fabric that we see, and then there's been a lot of back and forth about other types of slip systems that might occur. So I want to look at that in a little bit more detail. And so this is, again, that slide I showed earlier on, looking at this fact that in subduction zones, one way to still have your mantle flow direction be going towards the trench, but decouple that from the seismically fast direction is if you can get into this type B fabric. But it turns out, and so this relates to this very influential paper by John Corrado in 2001, where they experimentally measured these different fabrics in olivine, and they produced this plot. This is an updated version from 2006, where they said, okay, the type A fabric tends to plot at these water and stress conditions, and type B plots up here. So if you put a lot of water into your mantle and you also are at high stress, then you can have this different fabric. But it now seems pretty clear that it's pretty unusual to get to those very high stress conditions. And that's been shown by modeling and also from field observations. And then the other thing is that this has kind of led to this cottage industry of measuring fabrics in many more samples. And it also helps that the John Corrado sample study happened around about the time that EBSD really became available to a lot of people. And so that combination of things means that there have been, in the last 15 years or so, there have been many studies that have gone and looked at the LPOs of various xenoliths and orogenic footites and monophyllite to look at the fabric types. And over the years, there have been this accumulation of extension of the alphabet to these various fabric types that we identify. But in some sense, we've actually known this for a very long time. So this is a very classic paper by Carter and Ave Laumont from 1970. And they had what you could almost call the previous version of that John Corrado diagram, which is showing that the olivine, the dominant slip system in olivine, changes as a function of temperature and strain rate, and also as a function of the confining pressure. Right. So this here is the type A or easy slip system. This, I think, is the type D. And so actually, what this diagram does not, this one, I think the consensus now is that this is kind of one way of looking at the data, but there are other things that matter. And two of the things go back to this very early work in 1970, which is that the pressure and the temperature should also be playing a role. Another thing that we know now, so this is some data from Katsu Mishibayashi's lab in Japan. So he has a very recent study in 2016 presenting a compilation of fabric data for a whole bunch of different prototypes. And so this is this thing now that with EBSD, there's just been this explosion in data that's available. And so uniquely in this study, they have, so this is a map showing the different field localities. And then this shows the number of samples they have from the different localities. So this is, 241 is still a huge number of samples to have in one study. And relevant to this group here is that for trenches, they have 144 prototypes that they analyzed. And so if this whole type B hypothesis were correct, we would expect that we would see dominantly type B fabrics in those trench prototypes. This is a summary figure in the paper just showing that they, in all of the samples, they find all of these different fabric types. And they also include the seismic velocity calculation for one component. And then they also developed what they call a fabric index, which allows them to look at histograms of the different fabric types that they have. And so if type B slip dominated at subduction zones or at trenches, then we would expect, so the fabric type is up here, so there's B is here, A, D, E, C. This is the way in which they're doing this is a little bit complicated, but the main take home I want you to have from this is that trench prototypes are plotted here, and there's actually an impressive number of samples in this, and the most dominant fabric that they're seeing is this type A, or the easy slip in olivine. So I think that, and then there are, scattering. This AG type is probably related to meld, and then there are some other, the D type as well. So one of the things that we're seeing, yes?
So what are trench prototypes? How do they get there? Are they four?
Yeah, so that is another good question. So Terry's question is, what are trench prototypes? And these are, so the samples, these I think are almost all essentially 4-arc prototypes because they're not including any xenoliths in the data set. So they have samples from the Mariana Trench, the Tonga Trench, and those are all samples that have been collected either by dredging or diving from the trench. And so I would say the best approximation of what those are 4-arc. But if you look at the results from Eric Nella's study with Peter Van Kekken, if you're going to find B-type fabric anywhere, it should be in the 4-arc. So I think this is really, this data is really convincing that B-type is not the explanation for what's going on, I think, anywhere in the trench because of what they're showing there. So how long do I have? We have 20 minutes? Okay.
Yeah, so you should maybe 10 more minutes.
Okay, so I am going to, okay, let me put this up then. So this is just to finish that point. So this is this summary figure from Eric Nella's paper saying that from all of the geodynamic modeling they did to get to the stress and the water content you need, if you're going to see B-type fabric anywhere, it's going to be over here in the nose of the wedge. And the best observation we have now for samples from that region is that they are not showing that fabric type. And then on top of that, we have this fact that we do see other fabric types, and I think it is still an area of very active work to understand what all the things that are influencing the different CPLs that you see in periddotites. And also this this study by Katsu Mishibayashi. Let me just skip. So this, I think this is kind of one of the best databases that are out there. So one of the limitations we have at the moment with the olivine CPO data is that even just for the data that's being collected by EBSD, where people have gone and measured the LPO, which means ultimately you're producing, for every point in your map, you have a set of 3 Euler angles that tell you the orientation in your frame of reference. That those data sets themselves are essentially never published with the papers. And so one of the limitations we have at the moment is that it's very hard for anyone else to go in and to start treating these as a database of fabrics and to start playing around with them and really looking at the large scale, say, statistical properties of these different data sets. And this is something that the community recognizes at the moment. There's been some push to develop a database framework for which would allow EBSD data to be submitted, and so that people can start accessing this. But this is something, for geochemistry and other areas, online databases where you can go and download data sets. The limitation right now with all of this olivine work is that you basically can't go and download this. You have to email the individual authors, and not surprisingly, sometimes you get back the response, my grad student collected this, I'm not sure where the data ended up, things like that. So, I think in the next 5 years, we're moving towards a model where there will be a standard way that these data sets can be uploaded. Some of these data sets, in an individual sample now can be several gigabytes of data. So there is also kind of a size problem, but you also need to have the metadata to understand the orientation that this data is reported relative to. And then there's a bigger problem if you go back to the stuff that predates EBSD. There's some great fabric stuff reported in the older literature, really carefully collected by UStage, but the data that's forming those contour plots is basically gone. And so another kind of limitation is that it's really hard to mine the historical data in this case, because you just can't do anything more than show that pole figure that they produce, because the data on which it's based is just not available. So, hopefully moving forward, we will at least have a standard way to look at all of this. But, I think we're still, yeah.
Before you move from that slide.
Yes.
What about the periddotites and high pressure metamorphic rocks that do show a B fabric?
Yeah, very interesting, isn't it? Those are from this one locality that Katsu has looked at, or there may be 2 localities there. And they're also in the original Jung and Corrado paper, they report a couple other occurrences of B-type fabric, and I think they tend to be in high pressure settings. Yeah, there are lots of great questions to ask about, looking at this figure saying, okay, like why, let's look at other HP settings. Why are we getting that fabric type? Does that relate to the mantle flow, or is that something related to emplacement? Trying to get better constraints on the pressure, temperature, water content, melt content. There's a lot of parameters that also need to be constrained in this case. So for the LPO side of things, the last 15 years or so, we have a lot of great observations that have come out. To some extent, they've disproved the models that are out there, in that we don't have a really good framework to predict when you get different LPO types. and so that is something that is an active area of research, and I think there's more that can be done experimentally. I think in terms of observations, we're limited more by the fact that it's hard to look systematically at databases of these samples because there's a lot of data that's been published in the last 15 years, but it's very difficult to actually interrogate that in bulk. And I think that's the limiting factor right now. And then the last thing that I'm going to show is linking this back to flow in the mantle. So this last thing, okay, so how do we take these observations and relate them back to flow and anisotropy in subduction zones? And my reading of the literature on shear wave splitting and how to interpret these different signals in the end is that mantle flow is complex in 3D. And so if you want to try to relate the seismic anisotropy observations to a mantle flow model, what you need to put in there is a model, right? So here's just an example again from Torsten's work of showing a complex flow field around a subducting slab. But if you want to understand how that relates to the splitting, you need to have a model that incorporates olivine textural evolution. And this is something that's been looked at mainly in the ridge setting because it's actually been hard to just benchmark a model that works for the simple scenario of corner flow beneath a mid-ocean ridge. So this is a corner flow model. This is now, we're back in a ridge setting. This is upwelling beneath the ridge and then moving along off axis. And this is a really nice study from 2009 by Castlenow et al., where they compared a series of different models that are out there. So VPSC, this viscoplastic self-consistent model, has been very popular in the literature. There's also G-Rex, which is another commonly used model, and they varied some of the parameters. And they show that basically you can get a range of different predictions in terms of the orientation of, this is only showing the olivine A-axis. And so in comparing these models, they show differences in the prediction of the olivine A-axis orientation and also the magnitude of that fabric. And so I'm just going to end by saying that I think it would be good to see some of this also applied in a subduction zone setting. It's obviously, there's uncertainty just with the corner flow model, so it gets kind of worse if you're going to put this in a more complex flow field. But I will just put a plug for some work led by Lars Hansen, which was taking a set of experiments. So this is the top video is the LPO evolution as a function of strain in experiments. And then this is a model that we developed that also shows the development of that LPO in the model. And that model is designed to be incorporated into geodynamic models. And so there is the potential out there to take a model like this and try to couple that into a subduction zone model and try to predict, to try to match some of the seismic observations to the flow that we would see based on olivine fabrics. And I will leave it at that, which is to say, I think there's an agreement that the shear wave splitting that we see is due to olivine alignment during mantle flow. That bit's not uncertain. But we see that a range of slip systems are activated in olivine. And we know that things like pressure, melt, temperature, water play a role, but we don't have that really well mapped out at the moment. And that, looking in aggregate at the seismic observations for subduction zones and also some of the modeling, that is a complex flow field. But ideally, by taking these micromechanical models, we might be able to at least get a better fit between the seismic observations and what we understand about the flow field. Okay, thank you.
Questions from students and postdocs? Not all at once, please.
Do people make deformation mechanism maps for the different slip systems, just for olivine?
So it's not a direct correlation like that. So when olivine is deforming, we say, okay, it's deforming by this slip system. In fact, you have to have multiple slip systems active to accommodate the deformation because you can't open up voids in the rock. So the requirement is that you have 5 independent slip systems that are active. And so what we're actually saying is that the easy slip system is dominating. for example, the 100 on the 010 plane is dominating relative to the other ones, but there are other slip systems active, and so you're not doing a direct map. You can plot up the strength of the different slip systems so there've been measurements made on single crystals where they've activated a specific slip system, and that's actually how we know like the easy slip system is the easiest one to activate in pressure temperature space. But in terms of plotting up an individual flow law, it doesn't. I mean, you could take that single crystal data, but in the end, the aggregate actually has a very different strength to looking at a single crystal because multiple slip systems are active. And because of the way also in the dislocation accommodated grain boundary sliding, that grain boundary sliding component is really important. And that's functioning as one of your independent mechanisms. And so you also would need to have that flow law. So deconvolving those things is really complicated.
So going back to that Miyabashi paper, so those are, you said most of them are dredge or submersible recovered samples for the peridotite?
For the trench peridotite.
The trench peridotite. Okay, so in a lot of these locations, it's oceanic subduction. Mm-hmm. So if you're getting peridotite, it's not necessarily coming from really deep in the mantle wedge where the pressures would be higher. Does that matter much? Like at what depth would you start expecting to see B-type fabrics based on that hypothesis?
Yeah, so it's a limitation of all of those trench samples that they're basically, the deepest trench is whatever, 9-10 kilometers. So that's kind of, you're still kind of well within the lithospheric, the very shallow lithospheric portion of the plate. And so, but the assumption is that the fabric that it has is kind of being frozen in from when it was at a higher temperature. So it's kind of, at the moment, it's like the best samples that we have available, but this is the limitation with the mantle samples, is that we don't have the ability to say, oh, I would like to get the sample that is from 50 kilometers depth, because that's really where I expect to see this fabric develop. We really only have kind of what's exposed in the trench or what comes up in the arc volcanoes, and those might be way too far back from the nose of the wedge to be sampling the right area.
So would you predict for the shallower parts to have an A-type fabric? Or what? I guess as you go down in depth, is it all supposed to be B-type fabric?
I mean, according to the modeling that Peter Van Kekken's group has done, they kind of say that whole nose should be, but I guess it also depends on if you say that's really only happening in the asthenospheric portion, or if that extends into the lithospheric portion. I mean, yeah, I think it's just, we've struggled with the Tonga samples to really assign the kind of recent geodynamic history, right? The one thing we know is that they're from like 8 kilometers depth in the trench, but to assign what path they follow to get there is difficult.
Yeah, just to follow up on that, I mean, most of those are spinel peridotites, right? So, meaning that they come from a certain pressure range where spinel is stable, so that...
So it's, except that, right, so the classic idea is that the shallowest part of the mantle, plagioclase, is the stable aluminous phase, and then at a 30-kilometer depth, you transition to spinel being the stable phase, and then eventually garnet. But that's actually incorrect in that spinel is stable almost all the way to the surface, because those experiments that say the transitions at 30 kilometer were based on the chrome-free system. And once you put chrome in spinel, and these are all chrome spinels, and you extend the stability field. So all you can say for the ridge and the trench samples, they are always spinel peridotites. So they're not, you never have garnet field stuff. But the shallower, you never see the transition to plagioclase field.
Depends on the fertility, essentially. So if you have more fertile, I mean, so if most of those are...
You only see it when you have melt addition.
Not yet.
Students and postdocs. Patience, patience. Uli was a follow-up on a question that was relevant. So. No, that's appropriate. Well, we can open it up. Christy had a comment first, and then we can go over there.
I was just commenting or continuing the spinel to plagioclase transition conversation. We've looked at experiments to look at that transition too, and there's other compositional variables besides the chromium that affects the spinel to plage transition, and it's actually, it's a fairly large gradient depending on the compositional variability of the host peridotite. There's some other factors like the sort of magnesium content and things like that vary with the width of the overlap between the two of them, but that's not, I don't think that changes the main points that you guys are talking about.
Maybe you have already tried to answer my question, but at the beginning you showed that the anisotropy, seismic anisotropy, suggests is mostly B-type of fabric. And then at the end, you showed all the peridotite that has been recovered, has been studied, does not show that B-type.
Yeah.
Does that mean that the seismic anisotropy has not yet been explained?
I would say it is not explained. It has not been explained, or that B-type does not function as an explanation, because all the evidence we have suggests that it does not seem that we're in the B-type regime, or also that it's only in a very small portion of the wedge that you access that. But Torsten looks like he was going to make a comment on that.
Yeah, I would like to comment on this briefly. Yeah, right. Thanks, you have the mic.
If Torsten has a comment related, he can go.
Can you just comment on this briefly?
I think it's important to realize that we're talking about subduction zone anisotropy here for the most part.
Yeah.
And if you look outside subduction zones, such as underneath large plates like the Pacific plate, the azimuthal anisotropy does seem to align with flow in the way that you would expect from A-type fabrics. So it's nice to see that the xenoliths also look a lot like A-type fabrics, because otherwise this match and this nice consistent explanation would just be a coincidence. And so now, just to emphasize that, so we have an understanding of LPO anisotropy that's consistent. It just happens that some subduction zones show these anomalous signals, and perhaps B is not the explanation for that.
Yes, I agree with everything you said.
Rather, it could be complex flow, which is what was maybe perhaps the first suggestion, going back to stuff that Chad Hall did in 2000, where they modeled A-type fabrics and strong along arc flow for Tonga, for example.
Okay, that was good because my question's related. So for the bulk of the upper mantle, do we think that's A-type fabric or a different type of olivine fabric? Because that's for a dry olivine, right? So most of the dredge samples seem to be showing A-type. Is that because of some surface bias, or I don't know if you have any feeling?
I think the majority of observations we have do show an A-type fabric, and so as Torsten just said, and that agrees. A-type fabric and the direction of the anisotropy being aligned with the plate motion, that all seems to agree. So in general, that does seem to be an A-type fabric. It is because the databases of these fabrics, there's Katsu's one and also one that David Mainprice has, but the actual databases are not published. It's hard to tell you percentages for that and subdivide it further by location. Like for ridge peridotite, there's only one study of which Uli is a co-author that's really looked at the fabric in abyssal peridotite that are directly from the ridge. But I think in general it is A-type, but there are ways in which you can activate different subsystems. And then you asked something else. Remind me. You said something at the end of your question.
Well, that kind of answers my question, but I'm just thinking because A-type olivine is predicted to occur at low water contents. Oh. So if the bulk of the upper mantle is indeed A-type, does that have implications?
It's also not clear. Okay, so this is the thing that I skipped over, which is observations from the Josephine prototype where we've measured the water content and we've measured the LPO. So many times, a lot of the studies that assign water contents, they base it on the LPO. So there's been a lot of measurements of LPO and then an assumption of what the water type is based on the fabric diagram. And the point of this slide is just to say, these are the water contents, and this fabric type is this wet E-type fabric, but it has low water. And so we do not find a correlation between the water content and the LPO. So, which is, right, so we're actually way down at very low stress for everything. We have a mixture of A and E type, but we're like in this regime. But it's not clear once you start really measuring the water content directly in your samples instead of assuming it, that how well this whole diagram plays out. And I think Whitney Bear and one of her students also have similar observations as well. That there doesn't seem to be a direct mapping in field samples with the water content.
Thanks.
Okay, so just I've got sort of three things to point out. One is that kind of somewhat following up on Thorsten's comment is that, and this might be for students and postdocs thinking of projects, is that there does seem to be this correlation in the interior of the plates, particularly oceanic plates, where you have this shear wave splitting, the fast polarization direction, tracking that mantle flow direction and surface plate motion. And then in subduction zones, as we saw today, and previously, you have this non-parallel orientation of that fast polarization direction observed from the shear wave splitting and the trench motion. And so there seems to be this zone around the subduction zones with which you transition from more complex shear wave splitting observations to more aligned. So something to think about is like what's controlling that transition of sort of normal or expected splitting to sort of the slab-driven mantle deformation zone. Sort of one thing, and then the other thing is I just want to point out for the folks interested in that, I will be here for the next 2 weeks, and I'll add some additional references to the sort of 3D, 4D project options. And then thirdly, myself, Manuel H. Vincenda, and Li-Jean Liu and Maureen Long are actually hosting a session on this at AGU this year through DI. So for the people working on that, just wanted to sort of plug that session.
Two more questions, one by Thorsten, but before that, or three more questions, one by Thorsten, one by Jim, and then first by me. Sometimes it's useful to actually show the actual observations of anisotropy rather than compilations from papers, although it's convenient to do that. The shear wave splitting in Japan in the arc and back arc is remarkably in agreement with standard two-dimensional corner flow. Because the splitting is perpendicular to the trench in those regions. Mm-hmm. It's robust, and this is both for local events as well as teleseismic, so it's a clear wedge signal. So if you want to go to one place in the world where a subduction zone behaves almost normal, it's in the arc and back arc of Japan. The story is entirely different for the fore-arc in that same region, where you all of a sudden, right where the heat flow is low, you go to trench parallel splitting. It's a very dramatic change that occurs right where we think the fore-arc corner is. Would you, based on your discussion, suggest that the flow in the fore-arc is trench parallel and that it's normal in the arc and back arc?
But from what you're saying because you think in that situation that you are basically in a type B fabric there?
Well, it's more easily explained by type B fabric than by flow, I think.
I mean, so I think it's possible in that case if it's really just in that fore-arc region. It's right. I mean, the limiting thing is how do you test that, right? So the ideal way would be to have samples from there. And then the other way is that I think we do need more lab experiments and better constrained field observations of what the conditions are when you access these different slip systems in olivine, right? So one of the arguments has always been that these boundaries are very poorly constrained. And you go back to the original Carter and Ave-Lallemant data, and there's a temperature effect, there's a pressure effect. And there's been more recent stuff looking at that pressure effect. So I think, it's a viable hypothesis there, but it's also, when we try to make measurements where we independently measure water and fabric, it doesn't agree with this picture. And so I think this picture is an oversimplification of how you activate the different slip systems.
The other thing I would just quickly comment there. Hang on. Doug, you're so eager.
that with shear wave splitting, with anisotropy, we're not actually measuring flow. I mean, you're looking at a shear deformation.
Yes.
And so it's possible that the forearc is not really flowing, but because it's so cold, but it's having a deformation fabric. That would be a result of a compressional deformation with a long strike extension.
Oh, that's an interesting idea.
A hint for those of you using the microphone: if you're at the same time trying to demonstrate fabric, your microphone does not work. Thorsten, Jim, Lara, lunch.
Yeah, two quick comments, and I think there are places, as Peter said, where the splitting looks quite normal on a range of scales. And for instance, North and South America, Colombia is another place, where if we had not known about the parallel alignment, we would have invoked the parallel part as the anomalous part due to flow, and the rest looks just like Mackenzie suggested in the 70s. And so I think it's going to be very interesting, as Margaret said, and as we've sort of come back to revisit this idea, and as you said in your talk, of exploring how much three-dimensional flow, and as as Doug just said, complexities in the flow can explain the patterns.
Yeah.
And then the other comment is that it's not just the azimuthal anisotropy. It is also radial anisotropy, which has a one-dimensional average in the Earth that provides a constraint for what is happening. And so particularly if you fold in the dominance of dislocation creep in certain depth regions, plus whatever fabric you think happens is being generated, and its depth dependence, then that needs to match the radial anisotropy that we observe, which is nice, right? Because it gives you another constraint.
Yes.
But then my question is, sort of assuming that we can do this 3D flow stuff, and we'll still be left with anomalous regions and subduction zones, what do you think about some of the other mechanisms that have been suggested to explain the trench parallel fabrics, such as crustal, like weird minerals in the crust that have a signature that might explain it, and there's a bunch of other explanations. So do you have a favorite alternative, assuming 3D flow, if properly modeled, doesn't cover it all?
I do not have a favorite alternative. I will say the one thing I completely avoided talking about in this talk is the role of melt. And I actually in the LPO figures cut out the one that the LPO that seems to be most influenced by melt, and that is definitely a candidate for influencing what's going on. And in an arc setting, you expect a lot of melt to be around, and the experiments and also direct observations of field samples show this different LPO when melt seems to be present. So I think that would be a candidate to include in models, and I just think we don't have a good. I think we don't have a good handle on how water changes the LPO. So if you want to say in a subduction zone setting, water is added, which it obviously is. It's just the exact way in which the different subsystems you're activating in that process, I don't think we have a good constraint on. And I think that, and there are other things, right? So like, viscous anisotropy, the inherited fabrics, what role that's playing, that could be another thing that might matter, right? So if the complex flow doesn't do it, maybe it's the past history of flow that is also playing a role. And then, it's just not clear, like, what combination of slip systems we're getting as we add water. And, what we've seen in the Josephine prototype is really small scale variation in the LPO. Does that matter at a bulk scale? We don't have a good constraint on that right now. So, you could also be averaging multiple things. But the first point you made about looking at other things like radial anisotropy is also really important, because that does give you another constraint that narrows down what is and is not viable. And I'm guessing Jim's going to follow along with that.
I mean, yeah, I think the pointing out the complexities, I think, is a really important thing, because I think it's pretty clear that seismic anisotropy, the observations of seismic anisotropy are super rich in terms of when you get down to really look in detail. There's a huge amount of variability that we can't explain very easily with simple models. And part of that, I think, is because it's very much an integrated effect of lots of different length scales of deformation that's happening. You have old deformation through the lithosphere that's encapsulated there, and then you have the present day deformation, and that's going to change spatially. And I think become increasingly clear that even in really simple regimes like the middle of the Pacific Plate, you do actually have flow regimes that are deviating from what our simple models might have suggested. And so continuing to really probe the seismic data in particular, I think it's really a ripe time to try to go back to some of the subduction zone work and really see whether we can reproduce kind of what they've done in Japan and other places to try to look in a bit more detail to better understand this problem. I actually had a question though that goes way back to the beginning of your talk.
Okay.
Which is, you mentioned that for the deformation mechanism, or sorry, for the fabric problem, dislocation creep versus
dislocation accommodated grain boundary sliding
basically doesn't, they're equivalent. Is that true in terms of actually the strength of the fabric and how that might map back to the amount of strain that went into it? Are they both equivalently efficient, I guess is what I wanted to ask, or is there actually a subtle difference there that
I think we don't know. Be good to have Phil in the room, because I think there's one line of thinking that would say that a lot of the rock deformation experiments have been in have had a large component of dislocation accommodated grain boundary sliding, and so I don't know how many experiments you can assign to dislocation creep, which is what you need to really compare the two. And I think that probably there's not enough data available to assess that.
Okay, Lara, last question. Sorry.
This may be a tough question to drop last, but what about hydrous phases? We've been thinking about this trench parallel signature, and I know that for a while anyway, people were thinking that maybe these very strongly anisotropic sheet silicates like talc or antigerite, if oriented on a dipping slab, could produce a trench parallel fast direction, either parallel to the tip of the slab, if it's like a layer, or within the outer rise faults. Do you have any thoughts on what the latest thinking is of that?
That those are not in the right location for where you're seeing the shear wave splitting. That you're not going to get the stability field for those things is not that deep, so that you might, and also you need to get a relatively large amount of it, right? So the only sheet silicate you have available in the mantle is phlogopite to do this, and so.
Okay, maybe I'm totally wrong, and maybe a mineral physicist can jump in and tell me, but talc and antigerite are very strongly anisotropic, right? And so there were a series of papers that sort of suggested that you could, in fact, have a layer of that sort of above the plate, parallel to the plate.
But my understanding is that the splitting is occurring over a much larger bulk volume than just that layer parallel to the plate, that you need it over a bulk area in the mantle. Subduction zone.
Which side are you talking about?
So if you would expect it to be either parallel, so this is the direction of plate convergence, and if you would expect it to be parallel or perpendicular. And let's just stick with the mantle wedge for now.
At which position, I think that's the question. Where do you observe this?
I'm just saying theoretically, what would you predict?
At what point?
If you were looking at the splitting here over the mantle wedge. Or, I mean, you could also say over here as well, in this case. I mean, as a general, what orientation? Just raise your hand if you think it would be parallel to the subduction zone. If both your plates are moving, converging. Okay, and then if you think it would be perpendicular to the subduction zone. So the expectation, the plate motion is going towards each other, is that it would be, the answer would be B, right? And as many of you in the room know, what the actual observation is that it is, that we see this trench parallel direction. So this is the observation. This is the Tonga Trench over here. This is a figure from Smith et al., 2001, which Doug is a co-author on, so you can ask him questions about it. But the main observation I want to highlight is this trench parallel splitting that was observed. And in this case, this is on the mantle wedge side, but the observations have also been made on the opposite side, and they are also non-intuitive. So this is now non-intuitive? Counterintuitive. So, okay, this is now the compilation from Maureen Long and Torsten Becker's paper in 2010, summarizing all of the observations that have been made. And again, here is Tonga down here, and this is this really nice example where on both sides of the trench you have this trench parallel splitting, which is not what we would expect based on the fact that we expect the olivine A-axis to be the slip direction and to that to be more or less lined up with the plate motion direction.
Jessica, you were probably going to say that, but I think it's a fair statement that it's not necessarily everywhere trench parallel either. Right? And we had a good discussion about that last week.
Okay.
And I think you can, it seems like the more data you add, the sort of more mixed up this becomes. And I think it's, one could make the argument that we don't know if it's true.
And then I will go into detail about how we look at these samples and how we relate those samples to the seismic properties. So this is an olivine crystal with it's an orthorhombic crystal, and it has three principal axes referred to as the A, B, and C axis, or also the 100, 010, and 001 axis. And I will use both terminologies in this talk. Raise your hand and ask me questions if it's not clear what I'm talking about as I go along. The key thing to take away from this image is that the A-axis in olivine is the seismically fast direction, and the B-axis is the seismically slowest direction, and the C-axis is intermediate. So this is, in terms of understanding seismic anisotropy, this is the key aspect, that you have an anisotropic mineral and that the seismic waves will propagate at different speeds depending on which direction it goes through the mineral. The other important thing is that during flow in the mantle, if you're flowing by a dislocation mechanism, then you will end up having a crystallographic preferred orientation, also referred to as a lattice preferred orientation. That indicates that you have slip on a specific slip system in olivine. So in this case, what I'm showing here is what we call often the A-type slip system, also called easy slip for olivine. And another way to talk about it is actually identifying what that slip system is. So this terminology, 100 with the square brackets, indicates the slip direction. So it is slipping in the 100 direction, or the A-axis direction. And then the 010 indicates the slip plane. So the plane that it is slipping on, outlined in red, is the 010 plane. And the way that we figure this out in looking at natural samples is looking at the pole figure, which is plotted at the bottom here. So this is an olivine pole figure showing this easy slip system. The maximum, so this is just a schematic, so this is showing a maximum approximately aligned up with the shear direction, so that is the slip direction. And this that is normal to that shear direction is the slip plane. And then the 001 plane, or the C-axis, is not dominant in this slip system. So this is the fact that when olivine is deforming by a dislocation mechanism, it results in an alignment because it is dominantly slipping on a slip system such as this one, is what is giving rise to seismic anisotropy in the mantle. And so we have this general model for the upper mantle. Okay. So this is the third in the rheology lectures. You heard last week from Phil Scammer, who gave an introduction on rheology and rock deformation, and then Uli Fowle gave a talk yesterday about rheology and focused a lot on deformation more in the diffusion regime and how that relates to seismic attenuation. And so I'm going to talk today about rheology, looking at how we relate measurements of seismic anisotropy to what we see in mantle samples, and what the relationship is between this seismic measurement that we can make and what is going on at the microstructural level. So this is, again, focusing on rheology in the ductile regime. So compared to what we saw in the previous talk this morning, I'm shifting us back down deeper into the subduction zone system, into the area where things are flowing by a ductile mechanism. There is certainly a lot related to rheology that was discussed a little bit this morning in terms of the rheology at that plate zone interface, but what we're going to focus on now is what's going on in mantle flow in a subduction zone setting, and what the constraints are from field samples in how we interpret the seismic observations that we have. So this is a photomicrograph of a prototype. This was actually collected from the Tonga Trench, from a depth of about 8 kilometers. It is an unusually fresh seafloor sample. You guys saw in the tutorial, the geology tutorial last week, you saw some of these samples that we have from the Tonga Trench. These are one of the few places where we have 4-arc samples really collected in situ. But what I want to focus on in these samples today is largely the olivine, which is most of what you're seeing in this image. There is a little bit of orthopyroxene in this sample, and there are trace amounts of spinel that are not visible in this image. Olivine here, you will see this gradation in the colors. That is an indication of subgrain boundaries. That is an indication of the deformation that has gone on in the sample. So when we are talking about flow in the mantle, we are looking at samples like these that are relatively coarse-grained, but they do have a lattice alignment, and this is something that we can measure and we can link to the seismic properties. So I'm going to start out and give you an overview of why we care about this in the subduction zone setting, that in the asthenosphere we have flow that is reflecting the current plate motion, and that will result in an alignment of the olivine A axis, because that is usually the slip direction, and that is also the fastest, seismically fastest axis. And then as you go to shallower depths in the mantle, we expect to get fabrics that are frozen in. And so this is the general schema, the general conceptual framework that we work on when we're interpreting the fabrics in olivine-rich rocks. And then this can be related to seismic anisotropy, and I am benefiting now from the fact that Ed Garnero posts a lot of images on his website, including this nice little GIF showing what happens if you have an incoming seismic wave that is goes through an anisotropic medium. So your collection of olivine crystals, as long as they have a relative crystallographic alignment, that is an anisotropic medium, and that will result in this shear wave splitting that he is showing here. So the end result of that is that you get this delta T, which is something that the seismologists can measure and tell us a lot about in terms of what the splitting is, the magnitude, the direction. And so this has been, this was hypothesized going back to the 60s that there should be seismic anisotropy, and there was a very nice experiment done on the East Pacific Rise in the 1990s. So this is one example of the results from this experiment. This is the ridge axis coming down here, the East Pacific Rise. So we are way out somewhere in the Pacific Ocean with the Pacific and Nazca plates spreading apart from each other. And these are the shear wave splitting measurements that were made by Wolf and Solomon. And you can see that they are lined up approximately perpendicular to the axis. And so that agrees with this model that the olivine A axis, the seismically fastest axis, records the direction of mantle flow. And because flow at a ridge to be going perpendicular to the ridge axis, seeing that this shear wave splitting, that the alignment was like this, was a nice corroboration of this model. So you've all had coffee. Pop quiz. At a subduction zone, an example being here the Tonga subduction zone, where you have two plates converging, what would you expect to be the orientation of your seismically fast axis of the shear wave splitting? Do you expect it to be parallel to the subduction zone or perpendicular to the subduction zone? So raise your hand if you would expect it to be parallel to the subduction.
Anomalous everywhere, or if it's normal, or what normal should be.
Yes. So, okay. So Torsten's point is that, so Tonga, which I'm pointing out right now, is this really clear example. But if you go over here to the Andes, you do have a change as you go along, and you can, as you look around, you also, it is perpendicular here, Cascadia. It gets very messy over here. So there is also variation in the measurements that have been made, and so I will say now that where I'm going to end up with this talk is that it is complicated in that I would say 15 years ago we kind of were looking for this simple solution, and that is going to be this B-type olivine fabric that I will show you in a second. And then it also became clear from modeling that was done partly by Peter Van Kekken's group that that doesn't solve the problem, because you also don't access that fabric type. And I think where it's being left off is that the flow field in these subduction zones is relatively complex. And there's modeling that's been done, including by Torsten, showing that you have very complex flow fields. And where we need to go with this, and this is where I'm going to end up in the talk, is coupling those two models that predict olivine fabric evolution and see if we can really match those observations using the current generation of modeling tools that are out there. So this is this observation now that is 7 years old, or I should say this is a compilation that Maureen and Torsten presented, showing these global observations that you do get the trench parallel splitting. You do also get some perpendicular, some stuff at various angles, and that that the flow of subduction zones, I think the consensus would be that it is a complex pattern, and that it has become, as I'm going to show you in the rest of this talk, that related to this, the rheology, we have the tools to do it, but there's still a lot that we need to do to understand how everything relates. So this is, so I showed you at the very beginning that the easy slip system in olivine, the most common slip system in olivine, is this A-type slip system, this 100 on the 010 plane. And then going back to 2001, there was a suggestion made that the way to explain this trench parallel splitting was to have this B-type olivine fabric. And so this is, again, just a schematic of showing what the pole figure would look like for that